ID, the Future, a podcast about evolution and intelligent design.
Hello and welcome to ID the Future. I'm Casey Luskin, broadcasting with Discovery Institute's Center for Science and Culture in Seattle, Washington. Today, I'm talking to Guillermo Gonzalez, a senior fellow at Discovery Institute who holds a PhD from the University of Washington in astronomy. He's had quite an accomplished career. He's discovered 2 extrasolar planets, published many peer-reviewed scientific papers, developed new fine-tuning arguments, and co-wrote the book, The Privileged Planet, How Our Place in the Cosmos is Designed for Discovery with Jay Richards. Today, we're talking with Guillermo about his contributions to the book, The Comprehensive Guide to Science and Faith, exploring the ultimate questions about life in the cosmos, which is being released by Harvest House. I'm a co-editor of the book, along with William Dembski and Joseph Holden. It's got contributions from many leading ID proponents, including Guillermo. And Guillermo, in a recent podcast, we talked about your contributions to the book on whether we live on a privileged planet and also how solar eclipses provide evidence for intelligent design. But you also have a chapter in the book on panspermia titled, Can Panspermia Explain the Origin of Life? So Guillermo, thanks for coming back on the show today to continue talking about your contributions to this book.
Sure, I'm enjoying it.
Okay, so in the Comprehensive Guide to Science and Faith, one of the chapters that I was most excited about actually was your chapter on panspermia. I think there are a lot of problems with panspermia arguments, and I think there's a lot of room in the ID literature to develop these arguments. I remember learning about panspermia when I was an undergraduate student at UC San Diego, and I'm glad to see that you are tackling this topic. So can you start for defining for our listeners, what exactly is panspermia?
So basically, panspermia is the transfer of life between planetary bodies through space. And so it originated in modern times in the 19th century, independently by Lord Kelvin and Arrhenius. And they each developed different types of panspermia using different mechanisms. So one of them involved the transport of life between the planetary bodies through space via rocks, just rocks blasted off the surface of a planet from an impact. And the other one via life riding on dust particles. So just being pushed around by radiation pressure from the sun. So lithopanspermia is transport of life on rocks and just basically orbiting around following gravity, like planets orbit around the sun. But radiopanspermia, you have to take into account the pressure from the sunlight also. So not just gravity, but sunlight pressure. Those are the 2 primary mechanisms for transport of life.
Now, you also divide panspermia up into sort of a local type of panspermia and then interstellar panspermia. So local panspermia is obviously where life can be transported within our solar system from one planet to another. Do you think the evidence shows that local panspermia is plausible?
Right. So let's start with local. So you have, say, a big impact on Mars. Impact ejecta gets thrown off from the impact. Some of it reaches escape velocity. So you need big impacts for these kinds of launches of material that leaves the planet with enough speed and enough energy, then it's going to go into interplanetary space. And so a number of research studies have been published calculating the trajectories of fragments that are blasted off the surface of a planet and following them around as they orbit in a planetary system, and then see how long it takes to smack into another body. And so the transport times between various planets has been now tabulated from these simulations. And typical transport times are in the hundreds of thousands to millions of years. Now, there is going to be a very tiny fraction of that material that gets transported very quickly because those are lucky shots. So you have the very small fraction of lucky shots. Something hits Mars, something may reach the Earth in only a few thousand years. But then you have to consider other factors as to whether you're going to actually infect a planet with life from that other planet. There are 4 steps that you need to consider. There's the initial launch of the material from an impact. It's going to have to be a large impact. The transit through space, and that's going to take some period of time, and the organisms are going to be exposed to radiation from the sun, from galactic cosmic rays, and also, in case of lithopanspermia, from natural radioactivity in the rock, from uranium, thorium, potassium-40, and then the arrival of the rock to another planet. Okay, so launch, transfer time, and then arrival. So arrival, if planet's got an atmosphere, meaning if it's potentially habitable, it's got to pass through that atmosphere. So it's got to be large enough to survive entry into the atmosphere, right? We see meteors up in the sky, meteor showers, and we see these flashes of light. Those are tiny fragments, tiny, usually most of them are the size of a grain of sand, just entering the atmosphere at high speed. Minimum speed of entry at the Earth's atmosphere will be about 11 kilometers per second. So small things like something the size of a grain of sand is going to burn up completely. You have to be something like the size of a quarter or so starting off. So some of it makes it to the ground. If you want to infect the Earth, say from Mars, things riding on dust grains are not going to make it. They're going to burn up in the atmosphere. So either naked bacteria, for example, or small sort of bacteria riding on, say, something the size of a grain of sand, they are not going to survive re-entry. And then finally, the fourth step would be colonization. There's probabilities involved with each of these steps, right? So some fraction of the launched material is going to have living or viable organisms or organisms in the dormant state, perhaps. That's going to be a small fraction that gets launched. So most of it is going to be just crustal rock that doesn't have any living organisms in it. Some small fraction of that is going to contain organisms. And then it's going to transfer through space over some extended period of time, most likely tens of thousands, hundreds of thousands of years for interplanetary. And all during that time, it's going to be exposed to radiation. It's going to enter into the atmosphere of the target planet. And if it's got to be large enough so that it doesn't burn up, so a rock or boulder size object can survive to the ground. And in the interior of something like, a large rock, actually, it's not going to be very hot when it reaches the ground. It's still going to be cold from the coldness of space. It's only the surface that gets heated to melting temperature. So it's like flash heating because it doesn't get heated very long as it enters the atmosphere. So a large object's actually, even though it gets very hot on the surface, the interior remains cool. So potentially viable organisms could survive that aspect. Reaches the ground, and then they got to colonize. So somehow, any surviving organisms in the interior of that meteorite now are going to have to find the right conditions, nutrients, composition of the atmosphere, say liquid water, that they can start colonizing, not just survive, but literally colonize. So maybe start multiplying. And so you're going to whittle down the probabilities there too, because you're going to have to find the right conditions at the target planet on the surface that are sufficiently close to what that organism had at its source planet, that it's going to be able to grow and multiply. And so each of these steps, of course, you're whittling down the numbers tremendously. The launch, the transfers through space, their entry onto the planet, and then the colonization. So I think the probabilities are very, very small, but for two planets that are close to each other like Earth and Mars, and that had probably similar climates early on. Mars, we know, was wet early on. And so if there's going to be a possibility of panspermia anywhere, it's going to be between Earth and Mars. And I think that will be a good test. I think these missions to Mars are useful because they could test the panspermia hypothesis. If we find any ancient evidence of ancient life on Mars, see how similar it is, for example, to Earth life. I think that will be an interesting research program. Another, I think, probable aspect of panspermia is the Earth reseeding itself. So the Earth did receive very large impacts early on. We see the record of that on the moon's surface today from those very large early impacts. The Maria, or seas on the moon, were large impacts. The Earth would have had even bigger ones because of its stronger gravity. So the Earth would have been sterilized after the origin of life, possibly by one of these very large impacts, but the large impact would have blasted so much material out into space, and a lot of it would have remained in the same orbit as the Earth. And the Earth would have been continually scooping up debris from that impact for a long time. And so it's possible that after the Earth cooled down from that impact, even if it had formed a steam atmosphere as a result of the oceans vaporizing, and then it cooled down after a few thousand years, it would have still had fragments from an impact raining down onto the Earth. So I think the most probable example of panspermia would have been the Earth reseeding itself. And second in likelihood would have been a transfer of life between Earth and Mars. I don't know if it's likely enough to be plausible, but I think we have to be open to that possibility, at least for that case.
So there's also interstellar panspermia, where life is transported between star systems at great distances. So what does the evidence say here? Can this sort of panspermia actually happen?
Now here, I think, is where the probabilities get really, really low. I discussed transfer times in the chapter, and our solar system aids in spreading life from the Earth because of the fact that we have a Jupiter. That greatly increases the probability of launching ejecta fragments from the Earth out of the solar system because of the so-called slingshot effect. We use that, for example, when we send probes to the outer planets and we do a slingshot so that we have a probe going very close to Jupiter, and then it gains speed on its way out. So any object comes close to Jupiter but doesn't hit it, gets slingshotted out of the solar system. And so the time scale for leaving the solar system is on the order of 10 million years or so. So you're going to be drifting around in the solar system for a long time, all that time being exposed to radiation. And then the transport through space, probability of hitting any kind of random star around us is very low. Transport times are, again, on the order of tens of millions of years, although there could be a lucky shot and probably on the low side, a few 100,000 years. But that will be an extremely tiny fraction of the material, having an almost direct line of sight to a particular planetary system that's near us. The typical fragment would take tens of millions of years to go to the planetary system. And then the capture, again, is aided if a target planetary system has a Jupiter like ours. It greatly increases the capture probability. So if it's just a planetary system with, say, Earth-sized planets but no Jupiter, its capture probability is much, much, much smaller. So both as a source of, say, lithopanspermia and for capturing rocks, having a Jupiter greatly aids that process. Now, what aids it even more is having a binary star system. We now know that some binary star systems do have planets around them. The probability is increased by a factor of about 100,000 if you have a binary system as compared to just a single star like our sun with a Jupiter. Really, binary systems are where the action is going to be as far as panspermia goes. If it's going to happen at all, it's going to happen for binary star systems. And having a Jupiter compared to not having a Jupiter is, again, another factor of 100,000 or so. So if you're talking about a single star with just an Earth or a couple of other terrestrial planets, just a so-called field star, it's extremely improbable that it's going to capture rocks with possible viable organisms. By far, the most probable systems for both launching rocks and capturing rocks are binary star systems. Now, even more probable is a binary star or any star in a star cluster, because within a cluster, the relative speeds of the stars relative to each other is relatively low, and that aids in the capture of these rocks. And so by far the most likely systems to be exchanging rocks are binary star systems within star clusters, especially early on when they're very young, no more than a few tens of millions of years old. Now, why do I say that? Because it's early on that you still have lots of debris in a planetary system from the formation process of the planets. Like I mentioned before, we see a record of that on the moon's surface from an early time in the early history of the solar system when the impact rate was much, much higher. Most of the craters you see on the moon actually were formed in the first billion years or so of the history of the solar system. Very little has happened to the moon's surface in the last 3.5 billion years. It's like an attic. You put it up there and it doesn't change. You're looking at a very ancient surface when you look at the surface of the moon. And so early on, when you have lots of impacts, that's the source of the impact ejecta, right? That's the source material for lithopanspermia is impacts. And so the most likely scenario, most likely cases are going to be binary systems within star clusters that are still young. If life originates early on a planet, it's most likely to be transported in the interstellar panspermia case, it's binary star systems are involved in both the source and the target. But even there, again, the transport times total from initial launch to capture by a planet are on the order of millions of years. It's still going to be the problem of all the exposure to radiation and the degradation of the DNA in the organisms while they're inside the rock drifting through space. I think that's the biggest problem. They're just going to be degraded too much during those long transport times.
So, Guillermo, what I'm hearing from you is that panspermia within the solar system is probably possible. But what about interstellar transport or interstellar panspermia? Do you think this is a viable model that the scientific community ought to be taking seriously?
I think interstellar panspermia is extremely unlikely. I can't say zero perfectly, but it's extremely improbable as a viable mechanism for transport of life. Experiments with life that we've revived from ancient strata on the Earth, going back thousands of years, show that even in carefully controlled laboratory conditions, the fraction that you can cultivate is extremely small, even intelligently guided by scientists in the lab. That tells us that even in ideal conditions, the probability of them surviving is, even if they're transported, is very small.
Okay, last question. Let's say for the sake of argument that panspermia can work to transport across vast distances in interstellar space. Does this explain the origin of life, or does it just push it back?
Even if you granted that it were possible, I think it does just push the question back. And then you have to ask, what better environment than the Earth was the source of life that was transported to the Earth? The farther you go back in the history of the galaxy, that becomes harder and harder because the galaxy was a more dangerous place, actually, early on in the history of the galaxy. So it just pushes the question back, and it wouldn't push it back very far, given the astronomical limits on the age of the galaxy.
Okay, well, thank you very much, Guillermo Gonzalez. There's a lot more detail in his chapters in the book, The Comprehensive Guide to Science and Faith. So I hope our listeners will go check it out. It's available on Amazon. Thank you so much, Guillermo, for sharing with us about panspermia today.
Thanks for having me. I enjoyed it.
Well, it was a very fun conversation. I'm Casey Luskin with ID the Future. Thanks for listening.
Visit us at idthefuture.com and intelligentdesign.org. This program is copyright Discovery Institute and recorded by its Center for Science and Culture.